Hi, welcome back. In this video, we'll deal with the topic point of contraflexure or point of inflection. So, happy learning, and if you haven't subscribed the channel yet, please do subscribe and press the bell icon. Here I have shown an overhanging beam with a uniformly distributed load over it. I have explained the different types of beams and the types of loadings in the second video on shear force and bending moment diagrams. So you can watch that video in order to have a clear understanding of the important types of beams and the types of loadings. So what is meant by an overhanging beam? If the end portion of a beam is extended beyond the support, then such a beam is known as an overhanging beam. Here you can see that the end portion of the simply supported beam is extended beyond the roller support. This is the overhanging portion. Such a beam is known as an overhanging beam. In overhanging beams, the bending moment will be positive between the two supports, while it will be negative for the overhanging portion. So at some point, this bending moment becomes zero when it changes from positive to negative or vice versa. In this case, the right portion of the beam is extended beyond the support, right? So the bending moment becomes zero when it changes from positive on the simply supported portion to negative on the overhanging portion. When the left portion of the beam is extended beyond the support, then the bending moment becomes zero when it changes from negative on the overhanging portion to the positive on the simply supported portion. And this point of zero bending moment is known as the point of contraflexure or point of inflection. In order to find out the point of contraflexure, we must know the variation of shear force and bending moments along the length of this beam. Here we have a uniformly distributed load with a rate of loading 2 kN per meter and the length of the UDL is 4 plus 2 which is equal to 6 meters. We know that for solving the numerical problems, we have to convert this UDL into an equivalent point load whose value will be equal to the product of the rate of loading and the length of the UDL. So, the point load will be equal to 2 into 6 which is equal to 12 kilonewton and it will be acting at the center of the UDL. This UDL is 6 meters in length. So, the center of the UDL will be at a distance of 3 meters from A and C. So, the point load will be acting like this and the point load is equal to 12 kilonewton. Let's now find out the reactions RA and RB. In order to find out these reactions, we have to consider the moments about the end A. We know that the moment at this end A is equal to 0. So summation MA will be equal to 0. Let's now assume a section at this end A. Now we have this RB and this point load on the right portion of this section. So the resultant moment at this section due to these point loads will be RB into 4 minus 12 into 3. How? This RB has the tendency to rotate this beam in the anti-clockwise direction like this with respect to this section, and this point load of 12 kilonewton has the tendency to rotate this beam in the clockwise direction like this with respect to this section, and any moment in the anti-clockwise direction on the right portion of the section will be considered as positive and any moment in the clockwise direction on the right portion of the section will be considered as negative. Therefore, the moment at this section due to this RB will be positive while the moment at this section due to this point load will be negative, and the moment due to RB will be RB into the perpendicular distance, so RB into 4, and the moment at this section due to this point load will be this point load into perpendicular distance. So the perpendicular distance from this point load to this section is 3 meters. Therefore, the resultant moment at this section will be equal to RB into 4 minus 12 into 3, and it will be equal to 0 because the moments about A will be equal to 0. Now we can find out the value of RB. So let's take this term to the RHS. So RB will be equal to 12 into 3. Now we'll take this 4 to the denominator. So RB equal to 12 into 3 by 4 which is equal to 36 by 4 which is equal to 9 kilonewton. Now let's consider the equilibrium of the forces. So summation Fy will be equal to 0, right? So Ra minus 12 plus Rb will be equal to 0. Now we know the value of Rb. So Rb equal to 9 kilonewton. So let's substitute 9 kilonewton in the place of RB. So RA will be equal to 12 minus RB, which is equal to 12 minus 9, which is equal to 3 kilonewton. Therefore, RA equal to 3 kilonewton, RB equal to 9 kilonewton. Let's now find out the shear force and bending moment values along the length of this beam. For that, let's consider a section at a distance of x meters from the end A. The shear force and bending moment at this section can be found out by considering either the left portion of the section or the right portion of the section. Let's consider the left portion of the section. On the left portion of the section, we have a reaction force and a UDL of length x meters. For solving the numerical problems, we have to convert this UDL into a point load like this, whose value will be equal to the product of the rate of loading and the length of the UDL. The rate of loading is 2 kilonewton per meter, whereas the length of the UDL is x meters. So, the point load will be equal to 2 into x, and it will be acting at the center of the UDL. Here, the center of the UDL will be at a distance of x by 2 from the end A and from the section. So, it will be acting like this. So, on the left portion of the section, we have a reaction force RA acting in the upward direction and a point load 2x acting in the downward direction. Let Fx be the shear force and Mx be the bending moment at this section. Shear force is equal to the algebraic sum of the forces acting either on the left portion of the section or the right portion of the section. So, here we have considered the left portion of the section. So, it will be equal to the resultant of the forces on the left portion of the section. So, the algebraic sum of the forces on the left portion of the section will be equal to plus RA minus 2x, because any force acting in the upward direction on the left portion of the section will be considered as positive, while any force in the downward direction will be considered as negative. So, the shear force at this section will be equal to RA minus 2x, which is equal to 3 minus 2x. RA is equal to 3 kilonewton. So, just substitute 3 in the place of RA. So, 3 minus 2x. So, the shear force at this section is 3 minus 2x. Now, you can vary this distance x of the section from the end A in order to find out the variation of shear force between the points A and B. Now, at the end A, x equal to 0, right? So, Fa will be equal to 3 minus 2 into 0, which is equal to 3 kilonewton. Now, at this point B, x equal to 4 meters. So, Fb will be equal to 3 minus 2 into 4, which is equal to 3 minus 8, which is equal to minus 5 kilonewton. And we know that for a UDL, shear force varies according to straight line law. See, here you can see from this equation, you can see that shear force is a function of the distance x. That is, it is proportional to the distance of the section from the end A. So, it follows a straight line law. And at the end A, shear force is 3 kilonewton, and at the point B, shear force is minus 5 kilonewton. So, we can understand that somewhere between these 2 points, shear force becomes 0 when it changes its sign from positive to negative. Now, we have obtained the variation of shear force between the points A and B. In order to find out the variation of shear force between the points B and C, let's consider a section between these 2 points like this. Let this section be at a distance of x meters from the end A. The shear force at this section can be found out by considering either the left portion of the section or the right portion of the section. Let's consider the left portion of this section. On the left portion of the section, we have 2 reaction forces RA and RB acting in the upward direction and a UDL with rate of loading 2 kilonewton per meter acting over a length of x meters. For solving the numerical problems, we have to convert this UDL into a point load whose value will be equal to the product of rate of loading and the length of the UDL. So, this point load of 2x will be acting in the downward direction at a distance of x by 2 from the end A and from the section x. Now, on the left portion of the section, we have 2 reaction forces RA and RB acting in the upward direction and a point load 2x acting in the downward direction. Any force acting in the upward direction on the left portion of the section will be considered as positive, and any force acting in the downward direction on the left portion of the section will be considered as negative. Therefore, the resultant of the forces acting at this section, that is the shear force at this section, will be equal to plus RA minus 2x plus RB. Now at this point B, x will be equal to 4 meters, right? So FB will be equal to 3 minus 2 into 4 plus 9. Just substitute 4 in the place of x. So 3 minus 8 plus 9 will be equal to 4 kilonewton. And at the point C, this x will be equal to 4 plus 2, that is 6 meters. So FC will be equal to 3 minus 2 into 6 plus 9, which is equal to 3 minus 12 plus 9, which is equal to 0. Therefore, the shear force at B will be equal to 4 kilonewton and the shear force at C will be equal to 0. Now we can see that the shear force at this point B varies from minus 5 kilonewton to 4 kilonewton due to this point load, that is due to this reaction force RB present at this point. Let's now draw the shear force diagram so that this will be clear to you. Let's draw the shear force diagram. For that, we have to draw the baseline first. Now at this point A, shear force is equal to plus 3 kilonewton. So we'll mark it above the baseline like this. So this much is 3 kilonewton. Now at this point B, shear force is minus 5 kilonewton. So let's mark that point like this. Okay. So this much is minus 5 kilonewton. Now we have to join this point and this point using a straight line like this, because the shear force varies according to straight line law between the points A and B. See, Fx equal to 3 minus 2x between the points A and B. This shear force is a function of the distance of the section from the end A. So it varies according to straight line law. Now this shear force varies from a value of plus 3 kilonewton to a value of minus 5 kilonewton between the points A and B like this. Now at this point B, shear force changes from minus 5 kilonewton to plus 4 kilonewton due to the reaction force present at B. So the reaction RB is equal to 9 kilonewton, right? So minus 5 plus 9 kilonewton will be equal to 4 kilonewton. So we'll mark it using a straight line like this. Now this is 4 kilonewton. Now the shear force variation between the points B and C is also according to straight line law. So here also the shear force is a function of the distance from the end A. And at the point B we have shear force equal to plus 4 kilonewton and at C we have shear force equal to 0. So we can mark this variation using a straight line like this. So shear force varies from a value of plus 4 kilonewton to 0 between the points B and C according to straight line law. Now you can shade these regions and mark it as positive, negative and positive. From the shear force diagram, it is clear that at this point D, shear force has become 0 after changing its sign from positive to negative. Now at this point D, shear force will be equal to RA minus 2x, because we have to convert this UDL into a point load whose value will be equal to 2 into x, and it will be acting in the downward direction. So at this point shear force will be equal to 3 minus 2x and the shear force will be equal to 0. So 2x will be equal to 3 and x will be equal to 3 by 2, which is equal to 1.5 meters. So at a distance of 1.5 meters from the end A, shear force is equal to 0. Let's find out the bending moment variation along the length of this B. We know that MA equal to 0. In order to find out the variation between the points A and B, let's consider a section at a distance of x meters from the end A. The bending moment at this section can be found out by considering either the left portion or the right portion. So let's consider the left portion of the section. So here we have a reaction force acting in the upward direction and having a tendency to rotate the beam in the clockwise direction with respect to this section, and a point load 2x acting in the downward direction having the tendency to rotate the beam in the anti-clockwise direction like this with respect to this section. and any moment in the clockwise direction on the left portion of the section will be considered as positive, and any moment in the anti-clockwise direction on the left portion of the section will be considered as negative. So, the moment at this section will be equal to Ra into x minus 2x into x by 2, because moment is equal to the product of the force into the perpendicular distance. So, the moment at this section will be Ra into perpendicular distance minus 2x into perpendicular distance. So, mx will be equal to 3x, that is Ra is equal to 3. So, let's substitute 3 in the place of Ra. So, 3x minus 2x square by 2. So, it will be equal to 3x minus x square. So, at this section, moment will be equal to 3x minus x square. Now, at this end A, x equal to 0, right? So, MA will be equal to 0. Now, at the point B, x equal to 4. So, MB will be equal to 3 into 4 minus 4 square, which is equal to 12 minus 16, which is equal to minus 4 kilonewton meter. So, at this point B, bending moment is equal to minus 4 kilonewton meter. From the shear force diagram, we found out that at the point D, that is at a distance of 1.5 meters from the end A, shear force is equal to 0. Let's find out the bending moment at that point also. MD will be equal to 3 into 1.5 minus 1.5 square, which is equal to 4.5 minus 2.25, which is equal to 2.25 kilonewton meter. Therefore, at the point where the shear force is 0, we have bending moment equal to 2.25 kilonewton meter. In order to find out the variation of bending moment between the points B and C, let's consider a section between these 2 points. Let this section x be at a distance of x meters from the end A. The bending moment at this section can be found out by considering either the left portion of the section or the right portion of the section. Let's consider the left portion of the section. On the left portion of the section, we have 2 reaction forces acting in the upward direction, that is Ra and Rb acting in the upward direction and having the tendency to rotate this beam in the clockwise direction with respect to this section, and a point load 2x acting in the downward direction and having the tendency to rotate the beam in the anti-clockwise direction with respect to this section. Any moment in the clockwise direction on the left portion of the section will be considered as positive, and any moment in the anti-clockwise direction on the left portion of the section will be considered as negative. Therefore, the moment at this section due to these reaction forces Ra and Rb will be positive, whereas the moment at this section due to this point load will be negative. Therefore, the resultant moment at this section will be equal to Ra into x. X is the perpendicular distance between Ra and the section, minus 2x into x by 2. X by 2 is the perpendicular distance between 2x and the section, plus Rb into x minus 4, because x minus 4 is the perpendicular distance between the section and the reaction force Rb, which is equal to 3x minus x square plus 9 into x minus 4. Now, at this point B, we have x equal to 4. So, when x equal to 4, MB equal to 3 into 4 minus 4 square plus 9 into 4 minus 4, which is equal to 12 minus 16, which is equal to minus 4 kilonewton meter. At this point C, x will be equal to 6 meters. So, MC is equal to 3 into 6 minus 6 square plus 9 into 6 minus 4, which is equal to 18 minus 36 plus 18, that is 6 minus 4 is 2, 9 into 2 will be 18. Therefore, at the point C, bending moment will be equal to 0. Let's draw the bending moment diagram. So, we will mark the baseline first. Now, at this point A, bending moment is equal to 0. At B, bending moment equal to minus 4 kilonewton meter. At D, where the shear force is equal to 0, we have bending moment value equal to 2.25 kilonewton meter. Since the value of bending moment at the point B is negative, we'll have to mark it below the baseline. And the bending moment varies along the entire length of the beam according to parabolic law, because from these 2 equations, that is between A and B as well as between B and C, we can see that bending moment is proportional to the square of the distance of the section from the end A. So it varies according to parabolic law. And we have to mark this variation using parabolic curves. So let's mark the variation of bending moment between A and D first. So it varies from a value of 0 to a value of 2.25 at the point D. Now from the point D to the point B, bending moment varies from a value of 2.25 to minus 4 kilonewton meter. So the curve looks like this. Okay. Now from this point to this point, that is from the point B to point C, bending moment changes from minus 4 kilonewton meter to 0. So the curve looks like this. Like this. And you can shade these two regions and mark it as positive and negative. From this bending moment diagram, you can see that at this point E, bending moment has become 0 after changing its sign from positive to negative. This point is known as the point of contraflexure. The point of contraflexure or point of inflection is the point where the bending moment is 0 after changing its sign from negative to positive or vice versa. Here in this case, we can see that bending moment has become 0 after changing its sign from positive to negative. So let this point E be at a distance of x meters from the end A. So at this point, the bending moment will be equal to Ra into x minus 2x into x by 2. So 2x into x by 2 will be x square. So the bending moment at this section, that is at this point E, will be equal to Rax minus x square, and this will be equal to 0. So Ra is equal to 3 kilonewton. So 3x minus x square equal to 0. So x into 3 minus x is equal to 0. But x can't be equal to 0 because at x equal to 0, the bending moment is not changing its sign. So x can't be equal to 0. So 3 minus x is equal to 0, which means that x equal to 3 meters. Therefore, at a distance of 3 meters from the end A, the bending moment is equal to 0, and this point is known as the point of contraflexure. So the point of contraflexure is at a distance of 3 meters from the end A. You can also see that the bending moment is maximum at the point where the shear force is 0 after changing its sign from positive to negative, and the maximum value of bending moment is equal to 2.25 kilonewton meter. These are the shear force and bending moment diagrams of an overhanging beam with a uniformly distributed load over it. In the shear force diagram, you can clearly see that at the point D, shear force has become equal to 0 on changing its sign from positive to negative. And at this point, the bending moment is maximum. This point E is known as the point of contraflexure, where the bending moment has become equal to 0 on changing its sign from positive to negative. Please do like and share the video and subscribe the channel. Thank you.